we considered manufacturing procedure for glass fibers. Uh, you can produce strands of glass fibers, or you can chop it into smaller pieces to produce whiskers, which are discontinuous fiber reinforcements. And there are various commercially available fiber glass fiber types. It's possible to produce woven glass fabric reinforcements as well. And now we will look into these different types of available glass fiber forms. What are the available, commercially available glass fiber forms? That's the question. The main type is strands. It's a group of a bundle of glass fibers. There is a standard on this. In general, there are 204 or more fibers gathered together in a strand. This is referred to as an unwoven form. Three main unwoven forms can be considered. These are rowing, glass rowing, chopped strands, and chopped strand mat. These are main unwoven glass fiber forms. They are shown in these pictures. Glass fiber rowings are strands wound around a cylindrical package as shown here. These are standard strand forms, these two. Now they are available as raw materials for further production of composite structures. A second unwoven form is chopped strands or whiskers, glass whiskers. During manufacturing, processing of glass fibers, these strands are chopped into shorter lengths, and then these chopped strands are produced as reinforcements. Another unwoven type is referred to as a mat. This is known as a mat form. Chopped strands are used to produce this chopped strand mats. These chopped strands are mixed with a resin type of material, and then they are spread in a two-dimensional fashion. After the resin solidifies, you have a layer of reinforcement like this, which involves these chopped strands in a resinous material, binder material. That's referred to as chopped strands mat. These are all unwoven forms of glass fiber reinforcements. Woven reinforcements are produced by weaving methods of textile engineering, and we will consider three different forms here. One of them is referred to as woven rowing. A woven rowing is a fabric, and continuous strands are woven into two mutually perpendicular directions. So you have a plane of reinforcement. Woven cloth is similar to woven rowing, but this is produced from yarns. So what is the distinctive feature of yarn? What is the difference between a yarn and a strand? Woven rowing is produced from regular strand. Woven cloth is produced from yarn. And what's the difference between a yarn and a strand? Yarn is the twisted form. Actually, that's the difference. These are twisted fibers. Now, these two are 2D reinforcements. The reinforcement possesses bidirectional properties. And a third fabric type is also mentioned here. That's called woven rowing mats. A chopped strand mat is bonded with a woven rowing. Components here in a woven rowing mat are chopped strand mat and woven rowing. They are bonded to produce a woven rowing mat. Now, this slide may clarify the picture actually. This is woven rowing and it has bidirectional reinforcement features. This is woven cloth. It's produced from yarns. And a glass fiber woven rowing mat is shown. The components in this particular reinforcement are actually woven rowing, shown here as chopped strand mat. So that's somewhat stronger reinforcement. And these are starting materials. They have to be integrated into the matrix when it's in liquid form, of course, and then that structure is consolidated, it's heated, and after curing and cooling, you have a strong composite structure. Any questions or comments on these types of commercially available types of glass fibers? We have unwoven forms as well as woven types. Second group of fibers we can consider. These are carbon fibers or graphite fibers. Carbon fibers are stronger materials, as I mentioned. A range is given here for elastic masses from 200 gigapascals. This is for strength, and it can go up to 4,000 gigapascals. If you go back to this slide on properties of carbon, that's for strength, and some Moses values are listed for carbon fibers. Actually, so for this particular carbon fiber, tensile modulus is 231 gigapascal. That's pan carbon. It's pitch carbon. On the average, it's around 400 gigapascals. From 200 to 400, and there's an even higher value around 700. These are for tensile modulus. Strength values are also shown for a pan it's about 4,000 megapascals for a PAN carbon fiber. So it has a high strength material. And therefore, there is a wide range and even higher elastic modulus values can be attained. And it's possible to produce materials with high specific strength and high specific modulus. Low thermal of coefficient structures can be fabricated by using these carbon fibers, and they are used in a number of industries. The main use is in aerospace industry. There are two types of precursors for carbon fibers in carbon fiber manufacturing. Precursors are starting materials in carbon fiber manufacturing. There are two types of starting materials. One of them is PAN fiber, PAN carbon, and the other is pitch carbon. PAN carbon is polymeric substance, and pitch is, as you know, is a byproduct of petroleum refining process. And there are different commercially available forms. On Wowen forms, these strands of carbon fibers are named as tow, and Wowen forms, fabrics of carbon fibers are also available. Similar to glass fibers, you can find on Wowen or Wowen reinforcements for carbon. A sample material, a brand Zoltec, is shown here. So this average value for modulus is commonly encountered, about 250 gigapascals for modulus, and this has an average strength value around 4,000 megapascals. So these are average values. Materials with higher strength and modulus values are also available. This is on Wowen form. It is a bundle of carbon fibers, strong material, but it is on Wowen form. But Wowen fabrics of carbon are also available. This is bidirectional fabric, and thus when you incorporate it into the matrix material, and when you produce a ply out of this, there is going to be reinforcement in mutually perpendicular directions. High strength or modulus in this direction, high modulus in the perpendicular direction, and in all directions in between, you'll be able to compute high modulus of elasticity. But as an engineer, your task is to quantify this distribution. What is the modulus of elasticity in this direction? You need to use the underlying theory for such lamina or plates to determine such material properties in arbitrary directions. Any questions on this? There's a video on carbon fibers I want to show. I was playing this video. I'm going to share this. I'm going to play the video file on carbon fibers. I guess you can see the screen video file.
We develop and manufacture lightweight, high-strength components for the automotive and aircraft industries. We support the efficient generation of wind energy, and we invest in the future. The material we work with is carbon. The starting material for our lightweight, high-strength components is a precursor based on acrylic fibers. Complex oxidation and carbonization processes convert this precursor into carbon fiber, a unique material used in high-performance textile products and a wide variety of composite materials. SGL Group is the only European-based carbon fiber producer to cover the entire value chain, from fiber to finished component. Our fabrics made from carbon, glass, or aramid fibers can be matched to any particular application and processed further as required. We produce carbon fiber-based multi-axial fabrics for a wide variety of high-quality products. These fabrics allow us to maximize the application-specific stability and stiffness of components while simultaneously saving material. Carbon fiber composite materials open up new applications where other materials reach their limits. Whether fabric designs with variable fiber orientation are required, or different types of weave combined with high-quality resins, we can match our materials ideally to the needs of our customers. Our core competencies cover the production and further processing of carbon fibers, as well as the engineering of carbon fiber composite materials. This leads to technical innovations, such as the automated braiding process. Despite their tremendous strength, carbon fiber reinforced components are less than half the weight of steel and weigh approximately 30% less than aluminum. In automotive engineering, the drastic weight savings achieved with CFRP components not only bring about new performance records, but also reduce both fuel consumption and CO2 emissions. SGL Group supports this innovation by developing processes suitable for large series production in automotive lightweight construction. Complex structural components in carbon fiber composites are indispensable in the manufacture of new generation large capacity aircraft with lower fuel consumption. With our engineering and materials expertise, we are a competent partner for the aircraft industry. We offer our customers tailor-made solutions and set new standards with our automated production processes. The SGL Group invests in future technologies. With our materials and process know-how, we help increase the efficiency of onshore and offshore wind energy plants. In close cooperation with the wind energy industry, we manufacture rotor blades from fiber-reinforced plastics in lengths of 60 meters and more. These blades are used in state-of-the-art wind turbines to ensure maximum safety and low noise levels, combined with high performance and cost effectiveness. As one of the world's leading manufacturers of carbon, SGL Group covers the entire value chain of carbon fiber products, from the precursor via carbon fibers, fabrics, prepegs, and preforms, to finished components in carbon fiber reinforced plastics carbon fiber reinforced carbon, or carbon ceramics. Carbon is the key to innovative, efficient, and sustainable solutions for the environment and our future. Carbon is future. SGL Group, the carbon company.
As also shown in the video, there are certain advantages, of course, of using these materials. So the fibers can be integrated into different types of matrix materials. Even the matrix material could be carbon fibers in a carbon fiber, but most of the cases, carbon fiber is integrated into polymeric-based matrix material. Now we can look into the production methods for carbon fibers, but I have to open the file first. Let me open this file. The summary of carbon fiber manufacturing is described in this slide. And as we have talked about, there are two types of precursor materials, PAN fibers and pitch fibers. PAN is a synthetic polymeric fiber, and pitch is the byproduct of petroleum refining processes. These fibers are produced at a different facility than the carbon fibers, and they could be produced by a different manufacturer, actually. They are also formed as strands, or this is called a tow for carbon fibers, and they have to be made available to the carbon fiber manufacturer, these precursor fiber materials. And additional processes need to be applied on these precursor materials before the carbon fiber manufacturing is finalized. There are three main processes in carbon fiber manufacturing. The first of these is referred to as thermoset treatment. There is heating and stretching of fibers in these processes. The precursor fibers are stretched while they are heated, and the temperature is raised to around 400 degrees Celsius. This is the first step for cross-linking, formation of bonds. Actually, we'll talk about it in more detail, maybe next week. A second step of heating is also needed, and that is called carbonization. Temperature is increased to 800 degrees Celsius in an oxygen-free environment to prevent oxidation. And this step removes non-carbon impurities in these fiber materials. In the third step, revitalization. Additional stretching is applied, and elongation up to 100% here is experienced by the fiber. And temperature is increased further. It's increased up to 3000 degrees Celsius. It could range from 1100 degrees Celsius to 3000 degrees Celsius, depending on the particular application. But this stretching actually ensures a crystalline orientation along fiber axis, and it results in the desired value of Young's modulus of the fiber. It's the revitalization process. After these processes are completed, additional surface treatments are applied to the fibers. This will promote fiber to matrix bonding in later manufacturing processes or steps. The diagram summarizes the manufacturing processes for carbon fibers. There are two types of main precursor materials: pan-type fibers and pitch-type fibers. There are three stages of processing: thermoset, stage carbonization, and graphitization. Temperature is raised in each step, and the precursor fibers are stretched. Surface treatment, epoxy coatings are applied. These are done to prevent friction and abrasion between fibers and to facilitate bonding between the fibers and the matrix material in later production stages. That's a general summary of carbon fiber manufacturing. Do you have any questions or comments on this part? Any questions or comments? These were the most commonly used fiber materials. Glass fibers and carbon fibers are most commonly used fibers in structural applications. But we can also consider other fiber types. One of them is Aramid and the other is ceramic fiber, and we can briefly consider the properties of these fibers as well. Aramid fibers may find uses in certain applications. Aramid is a certain kind of polyamide. Actually, it's a polymeric material. The word Aramid comes from a blend of words: aromatic, polyamide. There's a trade name. It's a commonly known trade name for Aramid fibers. That's called Kevlar. These Aramid trade name of these Aramid fibers is Kevlar, and this is produced by DuPont company, actually. It was initially produced to reinforce certain tires and plastics. Therefore, these are composite materials as well. Both woven and unwoven forms of these materials are available. They are used to reinforce the material, to improve strength and toughness properties, and to reduce the weight of the overall structure. Some of them might have a negative coefficient thermal expansion in the longitudinal direction. This will help design structures with minimal thermal expansion coefficients in certain directions. And this is applied for printed circuit boards, actually. And a number of different trade names are mentioned here: Kevlar 49, 29, and 149. These are trade names for such fibers produced by DuPont company. This particular one is a high modulus fiber, for example, Kevlar 149. In processing or production of aramid fibers, an acidic solution is extruded to a spinner. This is a device used to form fibers. And then this mixture passes through several orifices or small holes. We have shown this process for glass fibers, actually. And during this operation, the material or the aramid molecules are oriented in the longitudinal direction. This results in higher strength and stiffness in that particular direction of the material. These are examples for available commercially available aramid fibers. This is unwoven strand, aramid fiber strand or Wowen. That is woven fabric form of aramid fibers. They both can be used as starting materials in manufacturing of composite structures. Any questions or comments on this part? Another fiber material is boron. One original feature of this material is the actually Chancer Mazur's value. This is larger than those listed for glass fibers or carbon fibers or other types of carbon materials. So this is a particularly high value for modulus of elasticity. When these fibers have larger diameters compared to the other fiber types, they are going to offer resistance to buckling because of larger diameter. And they may have higher compressive strengths. And cost can be a concern here. The application of the material should justify the use of these structural components because it has a relatively higher cost. But it could be an alternative in aerospace applications. Boron fiber. And one final example, ceramic. When there is a need to design resistance to thermal effects, that is material of choice, ceramics especially. This is an oxide ceramic, alumina fiber or aluminum oxide fibers are available, as well as silicon carbide oxides. And these materials have particularly high melting points, melting temperatures. Carbides have a melting temperature around 2,800 degrees Celsius. For the oxide fiber, it's around 2,000 degrees Celsius. And they can retain their strength at high temperatures. Therefore, they are candidate materials. They can be used to produce metal ceramic composites, for example, for high temperature applications. And this could be turbine components, gas turbine engines. They are used in nuclear reactors, fission reactors, commonly. Or they can be used as furnace components in heat exchangers. These are different high temperature applications where ceramic fibers can be used in a metal matrix, for example, to improve the resistance against heat flux or thermal effects. But composites technology is needed to integrate this into metallic matrix to process these materials. And in order to determine the material properties, mechanical properties or thermomechanical properties, you need to refer to the underlying theory regarding composite structures. Any questions on this or other types of fiber materials in general? Now, one final remark here is on fabrics. We have already mentioned fabrics. For each fiber type, carbon, glass, Aramid, it's possible to produce unwoven reinforcements and woven fabrics. And woven fabrics are produced by methods of textile engineering. These are produced through weaving. And different weave styles are available and can be applied to produce multi-directional reinforcement. Certain weaving styles are shown here. This is named as plain weave, basket weave, twill weave. This microstructure will affect the overall properties, which can be determined by testing. And examples are shown. We have already shown this, actually. This is Aramid woven fabric. That's glass, and this is carbon. So you need to start with a certain type of reinforcement. It could be glass fabric type reinforcement. And then this has to be mixed with resin, liquid resin. It could be a thermoset type liquid resin. Certain layup techniques can then be applied to produce the whole composite structure. But the liquid reinforcement mixture, of course, needs to be solidified by means of heating and pressure application. These are the details of processing techniques, and we will talk about it in more detail. But this can be thought of as the raw material, starting material, or the reinforcement material, which has higher strength and margins of elasticity values in all directions, in the X direction and Y direction, or an intermediate direction. It is important to characterize these properties in different directions. And we will see how it can be done, how experimentally or computationally. These are woven fabrics. Non-woven fabrics are not as strong as woven fabrics, but they can still find certain applications where the forces applied or applied stresses are not that critical. One of them was chopped strand mats, where you mix chopped fibers with resin, liquid resin, and this can then be solidified to produce such a chopped strand mat. We have a random distribution of short fibers or viscous. But the properties can be improved with continuous fibers. Continuous fibers can be mixed with the resin material to fabricate a continuous strand mat, and this will have somewhat improved properties compared to chopped strand mat. We will talk about matrix materials as well, but up to this point, we have considered different fiber types: glass fibers, carbon fibers, basic manufacturing procedures. We have also talked about properties of other fiber types, woven and unwoven forms, and terminology associated with naming of these fiber reinforcement materials. All of these should be known. Do you have any questions or comments about this part? If you don't have any questions, this is the end of the lecture for today, and we will meet next time on Monday.